information on strikes. So you can click there, and if nothing is written, then there is no strike going on. Okay. Yeah.
Cambia. Tanto non lo vedranno. Questo è sbagliato il photo start. Cioè mi fido. Sì, è pure l'inizio. Vai. Ok, grazie, non lo sapevo.
Ripetere, non ho capito.
Bene. Qui...
Salta e basta.
Okay.
Può partire in spaghetti? La registrazione è a posto? Okay. Hello everybody, and let's welcome Valerio and Enrico. Enrico is a long-time Italian Pythonist. I've met him since the first Italian conference. And then Valerio and Enrico met in an Italian forum where you can speak about Python. So, just before you start crying for this great friendship which was born after Python, I just leave the word to our speakers. Thank you.
So, we decided to do this presentation about number crunching in Python because we feel there is a great tool to do that kind of stuff, but sometimes it's hard to focus on some details about memory layout and that kind of stuff. So, basically I start with scientific and engineering computing. That is to say, we'll see which alternatives we have, because when we want to choose a tool to do a task, it's better to know which are the trade-offs we have to decide. Well, then we wanted to do something about common floating point pitfalls. That is a very important topic when you have to do scientific computing, and is something that sometimes is not very deeply explained in university courses. But still, there was no time, so we decided to just remove it. I may advise, I strongly suggest this book, which is a great book. It's not very expensive because it's Dover Unabridged Publishing, so it comes from an older book, but it's still very, very, very actual. Okay, so that's the slide about this. Then I describe NumPy, the ND array, which is just the core of the NumPy library, and eventually we have, well, he has described some case studies that show how can be used NumPy, SciPy, and that kind of stuff. So basically, I got the shortest straw, and I'm doing the boring stuff, and he is doing the fun things. But anyway, I'm not lucky. So, what is number crunching? We are talking about computations of numerical nature. Basically, it's about floating point numbers, and sometimes it has this connotation of brute force, mindless, and evilness. Well, perhaps nowadays with huge data sets that are so relevant for all kinds of businesses, well, we have to accept that brute force does not mean mindless, and that number crunching has nothing to do with being mindless and brute force. So we declare we are not evil, we are chaotic neutral. Okay. What are the alternatives? This is very popular. MATLAB is being widely used in engineering, scientific computing. And it's an integrated development environment, very oriented toward numeric computations. It has lots of high-quality algorithms, a lot of packages. But I feel that general programming is somewhat limited. You don't have a very good module system. Well, you don't have basically a module system at all. So it's difficult to do things that are just outside its typical domain. Basically the same things apply to Octave as well, which is a clone, an open source clone, so at least it's not commercial and you don't have to pay the quite reasonable license that MATLAB requires. Then there is R, which is a very interesting open source project, which is very popular among statisticians, but I feel that that has also a poor general purpose programming support in the sense that well, it was created with one goal in mind, and that is where it's good at, okay? And then there is people doing numerical computation in Fortran and C++, and that are very low-level languages. Well, perhaps 20 years ago it was, or 14 in this case, high-level, but now is low-level if we compare to Python. They are very fast if you know how to write things, but I feel I think it's objective to say that they are more complex to use. Because they're so low level. And besides, sometimes if you do not do things the right way, you end up being not that efficient at all. So in general, there are these two points where you have either low-level general-purpose languages that are good for general-purpose programming, well, at least in the case of C++, or high-level domain-specific languages. If you have to do both things together, then you are a bit in trouble. Okay? Luckily enough, there is Python, which is a very good general-purpose object-oriented programming language. Okay? But also has very good libraries. It has a very good module systems, so you can make software engineering. But you have also numeric libraries that fit into the whole scheme and are very good to use. Besides, you also have EuroPython, which is just wonderful. That is a command line interpreter, I think that's popular. And the more recently, EuroPython evolved into Python Notebook that offers mathematical-like interactive documents, which we found very useful. In fact, we prepared lots of notebooks for the examples in this presentation that you can just download from a GitHub repository and run, basically. So there are all kind of libraries for scientific computing, starting from file systems, file-like file system for scientific datasets like HDF5. You can interface easily with database, of course, you all knew that. And specific libraries for machine learning, or optimization, or whatever you can think about. So it's not like you have to do everything by hand and reinvent the wheel. You have good libraries, but also a good support for general purpose programming. About the tools, of course, these are the main ones, and we also included these ones, which we decided, unfortunately, we had to leave out, because we didn't have enough time to put the example and the case studies. Still, you find the notebooks in the GitHub repository. So, why is so good NumPy? Basically, the idea is that you write very high-level code and you benefit from highly optimized libraries, because you have your code here, and then you call NumPy code, that calls matrix algebra libraries or whatever is relevant for the task, like MKL or Atlas. And these algorithms here are very fast because they are highly optimized, okay? And this stack here means that every improvement at every level makes your general application faster, okay? So, for example, if you put here something that uses your GPU, for example, then your application gets faster. But you reason at this level. You write code with NumPy in mind. And why it is so fast? Because basically, you have a very, very small Python overlay. I mean, Consider this. You want to multiply two matrices. You get the matrices, and you call the dot function that makes dot product between the matrices. That's the Python stuff. You load the name of the function. Okay, I should have not made such an import, but this makes easier thing. I should have called np dot. Then you load the operands, call the function, and store the results. Everything else is C, Fortran, whatever code. So that is very, very fast. And this is basically the layout of an ND array, which stands for n-dimensional array, I think. And you have a memory area, okay, of homogeneous types, objects. So that's different from Python lists usually. And then you have some property, for example, the shape of the array, which can be, for example, 4 times 3 matrix, okay, but can be more general than that. And there is the issue of behavior. So you have a lot of object-oriented stuff, methods of the classes, that is. So we will see in detail each of these elements here that make an array, an ND array. I just love this design. I find it that it's wonderful because it's quite a good object-oriented design, but it is also a very good compromise with the efficiency required for scientific computing. Okay. The first problem we have is that memory in a computer is linear. You don't have two-dimensional things. You just have a linear structure. But we want to reason about, for example, two-dimensional stuff. Okay, 2, 3-dimensional, but at least two-dimensional. Okay. So the first thing to understand is that the elements that we have in a matrix are somehow put in a linear structure, and you can use these two kind of representation. I mean, you can just store the columns one after the other, or the rows. That is C continuous, and this is F, which stands for Fortran contiguous, because that was the convention used by Fortran, and that is the convention used by C. So, since I love formulas, I tend to put a lot of them in presentation because, well, I'm a bit chaotic, as I told you before. But this is not really important to understand. This is the example relative to the picture here. So if we want to know which is the index in the linear structure, we have to do this kind of operation when these, the D, are just the shape of the matrix, okay? And so in this case, we have this quantity that considers the higher strides, and this is considered the lower, sorry, the higher shapes, okay, the higher elements here in the shape tuple, and this considers the low shapes of the low elements of the shape tuple, okay. This becomes can be abstracted considering the concept of stride, so we do not have to see that anymore, and we just have to consider that in order to get the next element, we have to use the stride. So, for example, this is the 0 element of the first row, and then we have this element here is just, well, I have the representation for the C, but anyway, would be here, okay? Basically, that's it. Strides are important because, in fact, you can think, it's a very general concept that you can use also with non-continuous memory layouts, which we will see in a few slides. Okay, so if you just think that the stride is the way to know which is the next element, then it becomes easier. Okay. The other thing to consider is that many times arrays are just fused over the same memory area. So in fact, when you do lots of operation, you are not allocating more memory, you're just reusing existing memory. Okay? This can be both a very good thing or a very bad thing, because if you do not realize that you are modifying a data structure, okay, you may have subtools, bugs. Still, the other way around would be quite too expensive to compute. And this is an example. So we create matrix here, okay, and then we take this is the transpose of the matrix, and we put it in another variable, okay. We modify here the transpose of the matrix, but we find that also the original matrix has been changed. This is because the transpose is not a new matrix, but there are two ND arrays that refer to the very same memory, okay. They have, in this case, well, the shape is 4, 4, but it was 4, 3. If this was 4, 3, this would have been 3, 4, okay? So that's just the transpose. We do not use more memory. In this other example here, we call the reval function that returns, well, let's say for now that returns a linear version of the matrix, okay? And we can access just an element, because now it's linear, we don't need a tuple anymore. This as well is a view over the matrix. Here we see that the original matrix has been modified, because the two elements here, 0, 1, 2, 3, okay? Still, NumPy does not require that all ND arrays refer to continuous memory. And this is very good, but can be also a source of problem because of the efficiency. Usually CPUs are very fast to work with continuous memory. They can load it very fast and process operation using instruction level parallelism, that kind of stuff. But it's not so easy to load things like this, okay? So sometimes you want to make memory contiguous. But anyway, this is very reasonable to do. And in this case, for example, we have a C-contiguous matrix. So we know that a column of the matrix, which is a perfectly reasonable item to take, in fact, is not backed by continuous memory. So NumPy, in fact, does not copy the elements. So the column is not a new does not use new memory. So here we take the row of the transpose. So we are taking the column. You see, if you just use one number in the slicing here, you take a row, okay? And when we modify it, we find that the original matrix has been modified as well. And now here we call the reval function again. This is a new matrix, okay, and it is not a Fortran matrix, so we know it's C-contiguous. And we take the transpose, and we take the first row of the transpose, that is the first column of the original matrix, and we modify it. See, we print it, so we know that we actually modified it. But the original matrix has not been modified, because reval guarantees that the array that returns has contiguous memory, is a linear object with contiguous memory. So, for example, depending on the kind of things you are doing, this can be very good for efficiency or very slow, because you're basically trading space for time. Okay? So you have to keep these things in mind. If you program NumPy stuff carefully, then you're going to be pretty fast. Okay, we have some timing afterwards. Otherwise, you're going to be pretty slow. Okay. So this is the last thing to know about ND arrays. There are subclasses. For example, the matrix subclass. And usually, when you just multiply two ND arrays, you are just making element by element multiplication, okay? Otherwise, if you create a matrix object, okay, from an ND array or in other way, that makes a dot product. So it behaves like you would think an object implementing a matrix would do. You multiply two matrices and you got the dot product. Besides, this does not make a copy, actually, I think. Okay, basic indexing, this is easy. You can just take index of matrices, okay? But you can also use slicing, so you can take all kind of blocks from a matrix, and this uses the original matrix memory, okay? But what we really like about NumPy is advanced indexing, okay? So we have this matrix here, and you can do all kind of things with strides, for example. So you can just take these elements, okay? And you can work just on those. You can, for example, set all of them to 1. This is called broadcasting. If you make an assignment and what you put on the on the left side somewhat makes sense. So, for example, shares one dimension with what is on the left side, or on the right side. Sorry, on the left side. Yeah, or it's just one element. Okay, you make this is very well doing one operation and it's very fast. Okay. This is another very good feature. This is the matrix, and we say, okay, A modulus 3 equals to 0. What is that? That is an array that has true or false. Basically, it's like a query, okay? You're querying in which positions of A, the element in that position is a multiple of 3. Okay? Since this is pretty unreadable, I usually do this, which returns a copy of the matrix with floating point numbers that are a bit prettier to print here. Okay? And so that's where we have multiple of 3s, as expected. Okay? Eventually, we can do this kind of assignment. There were 45 of them, and we just put a range of 45 that basically works like range. So here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Okay, just one instruction again. And if what you put here somewhat makes sense, then you can do all these crazy things. And the last thing is about the vectorized function, because essentially the trick with NumPy is not using for loops. Because every time you do a for loop for something like that, you are writing Python code. Python code is slower than NumPy optimized code, okay? Because when you are reasoning at NumPy level, you are calling Fortran or C. And when you reason at Python level, you are doing just Python, okay? So, for example, there is this function which take a function that reasons element-wise and returns a function that reasons matrix-wise. So, this make checker, range checker, takes 2 arguments here and returns a function that tells you -1 if the number is before the range, 0 if it is inside range with usual C conventions, and 1 if it is larger than after range, okay? Then we simply pass, vectorize the function returned by make checker, make range checker, okay? And we have a function f that we can call passing a matrix, and that works on the whole matrix. So that's the idea. As long as you can do this kind of stuff, you're going to write quite fast code. Okay, and now I stop, and we start with some case studies with NumPy, SciPy, and that kind of stuff. Thanks.
Can you hear me? Yeah? Quite sleepy, I guess. Anyway, so second part is number crunching in action. So the first things to say is that we are gonna talk to numbers. So a little bit of math inside, but anyway, I'm not going to give you all the details, just a pointer to the related arguments related to the different example. Before starting, what we need to get started? Well, a handful Unix command line tool. So those of you using Linux or Mac OS, you guys are done, but for Windows users, it should be the time to change, maybe. But anyway, it's up to you. Then, of course, Python, and IPython. And a DBMS, maybe. For instance, a relational one, such as SQLite3 or PostgreSQL, or a NoSQL one, such as MongoDB. Okay, so the first case study regards benchmarking, and in particular tries to prove the claim that in NumPy explicit for loops are not a good idea. In particular, we have two different examples. The first one is about the vectorization, and in particular we are trying to apply the sim function to the element of a matrix, and we're gonna see if which is the most convenient solution. And the other one is about the matrix vector product, so different implementations of the matrix vector multiplication. Okay. Oh yeah, just a brief introduction. For this kind of stuff, I used also, in addition to the previous tools, the SciTools, which is a sort of collection of libraries and functions built on top of NumPy and SciPy that provides some mechanisms, some already built-in functions for taking times or print tables of results, so stuff like that, without re-implementing them from scratch. So for instance, this is an example. SciTools.misc contains an hardware info function which returns the info of the hardware used for the experimentation. These are the information used in our examples. Well, let's start. So the idea now is to apply the same function to the elements of the matrix. So the first quite trivial solution is to iterate. Okay, in this case, I think that X corresponds to an array, not a matrix in this case. So the quite trivial solution now is to iterate over the element of the arrays using the sim function from the math standard library of Python. So this code is full Python code. The second solution, and maybe the third one, okay, let's introduce some difference. In this case, the sim function is the NumPy reimplementation, so we apply the sim function on an element but with a different one. And in this case, we use the math standard lib function but without importing in this function, so without wasting time in importing at every iteration. And the last solution is full a NumPy function, applying the sim function to the array one shot. So this should be the best solution as we expected, and in fact, let's see who's the winner. So NumPy wins. Oh, sorry. Well, excuse me. I need to, wow, too much transitions. Okay, so NumPy is the faster solution, and in particular, is 17 times faster than pure Python implementation. And without calling the y function, so not importing the scene function at every execution of the function, is almost three times better. Okay, so for now, okay, so this is the first result, but nothing new. Okay, let's go to the next example, the matrix vector product. Now, okay, so basically this is the math, the typical operation necessary to multiply a matrix for a vector. So the output, the final output of the matrix vector product is a vector itself. And then this is the code. In particular, I introduced also this code because it contains some details on how we have to deal with the comparison of floating point numbers. Because now we are trying to check if all the functions defined in the next slide returns the same stuff. So what we did was to sum all the values and the absolute values of the difference. So and we want to check if the values are equals. But to do this with floating point numbers, we cannot use the equal operation due to some representation and stuff like that. So this is quite a hint on how to do this. But anyway, let's go to the benchmarking. So I present these three functions together because this is the first one is the pure Python loops. So two explicit loops iterating over the entrance of the matrix and the vectors. And these two guys here are two sort of optimization without using explicit loops, but using instead map and reduce functions, so a sort of functional programming. But anyway, without going into the details about this, the idea now is to re-implement, try to avoid explicit loops, but we're implicitly doing all the stuff, all the same stuff. And finally, the dot function, which is the already presented function of the NumPy package. And the last one tries to check if NumPy is faster in single precision. So in this case, we have a matrix and a vector of a float 32 type. And who's the winner? In this case, the winner is NumPy dot, again, sorry, not my remote, that's why I make this mess. Okay. Okay, NumPy dot float 32. Okay, and maybe the interesting part here is that plain loops are worse. And in particular, this number means that we did on a matrix and a vector of 2,000 entries. So the matrix was a square matrix, 2,000 times 2,000. And we did 20 different execution for each function. And this number here means that the single execution of a plain loop is almost 2,050 worse than the NumPy implementation with a single precision number, so for float 32. So it's really bad. So explicit loops is not the good solution as we expected. Okay, so again, Well, now the idea is try to apply all this stuff in some more appealing applications, such as machine learning. Machine learning is a very interesting field, and in particular, machine learning means learning by machines. We are not going to talk to computers with machine learning, but what we're trying to do is to apply algorithms and techniques to gain insights from data or data set. The learning part of the machine learning stuff is usually divided in two different categories. We talked about supervised or unsupervised learning, and one of the most famous example of unsupervised learning is clustering, which is the example we will see in the next slide. Machine learning, as you may know already, is actively being used today, perhaps in many more places than you expected. For instance, there is some machine learning stuff running in your spam filtering for your mailbox. There is machine learning for ranking results for search engines, or in the preference selection, such as the ones proposed by Amazon, that states customers who bought this also bought that. This is machine learning stuff. Okay, so brief introduction for clustering, which is the second part of these case studies. Clustering in general is a type of, as I anticipated, is a type of unsupervised learning that automatically tries to create groups of objects according to their similarities. So it's sort of automatic classification of objects, and clustering may be applied almost to anything and almost to every object that you can compare. One of the most used algorithm of clustering is the k-means one. K-means is an algorithm that will find k clusters for a given data set. It's quite trivial and it's quite simple to implement. And the idea is that, and the main drawback, is that it is full automatic, but you have to specify how many clusters you want in output. So in some cases, you may not know how many clusters, so how many groups of objects you have to have after the execution. So this is basically the drawback. But it works in a lot of cases. So k-means, as we expected, is offered already built-in in the SciPy library. And in particular, there is a module, a library called cluster that contains k-means, for instance, and in particular two different implementations of the k-means and other clustering algorithms as well. So let's do a brief example on how to deal with clustering included in SciPy. We imported the modules we needed, and we created two matrices of random numbers that have the shape of that have the shape of 1000 times 2, both them. And then this is an excerpt of their content, randomly generated. And the last part tries to, in the first line, calls the vstack, which is a function that takes, in this case, two matrices and create an output matrix that contains the two one top of the other. And then we apply the k-means algorithm, and the SciPy implementation of k-means returns the variance and the centroids. Centroids basically are the central points of each clusters. So this is the stuff on which the k-means is based on. So if you have questions, you're more than welcome, but this is quite details that I'm going to skip. And then BQ is a function that for each point and for each point in the data set, so the features, assigns each point to the closest centroid. This is the aim of the function. This is the cool stuff. So we may plot all the data in using matplotlib, and this is the output. And the real cool stuff here is that we did this using EuroPython notebook. So all integrated into the browser, including the matplotlib stuff. Actually, there is an option you can use when you run EuroPython notebook. So, but it's well documented, so you may look at the documentation. And the green points here are the two centroids. So quite trivial, I guess. Anyway, let's do a little bit more interesting example. Yes, thank you. So here's the situation. You have, that's a sort of quite typical application of such techniques. You have a friend called as you like that wants you to take him out in the greater Portland, Oregon area, US, for his birthday. And well, you have a number of other friends going to come also, so you need to provide a plan that everyone can follow. The idea now is that your friend has given you a list of places he wants to go, and you have to, and this list is long, 70 establishments. So the idea is to optimize the visit of all the places according to their locations on the map. And to do this example, we also use the Place Finder API provided by Yahoo. Actually, there is a Google implementation of such stuff, but I didn't realize how I can use them without creating a web app. Yahoo provides availability for these APIs also for desktop application. But anyway, there is a way that is for sure simple. So this is the example of the API provided by Yahoo. You have a URL you may query. You have to provide the address and the name of the city, and it returns you the latitude and the longitude values for the location and in a JSON file. Okay. And now the point is, briefly, that we are trying to measure the distance. So we have to measure the distance of points corresponding to latitudes and longitudes. So working on a map, we are not able to use the quite standard measures, but we have to deal with the so-called spherical distance measure, which is implemented quite simple here using NumPy operators, sin, cos, and all the stuff like this. But the most important part here is that unfortunately the SciPy implementation of the k-means does not allow you to customize the distance function to use, because it uses a function which is built in, and that is the quite famous Euclidean distance between different points. So to do this example, we must re-implement the k-means from scratch, but it was not a big deal because the algorithm is quite simple, and this was the output, the final output of all the stuff. We got the map of Portland, we got the points of all the locations, and we applied also the points on the map. So we did the clusters, and that's it. Well, basically, after this, there should be another example that I'm going to skip because the time is, I'm running out of time, but you may find this on the slides. I may go to the most important part because I have 1 minute left. So the idea now is to calculate the inverse of the matrix, which is a quite trivial solution and a quite famous solution. And basically, it has many different possible solutions in maths. The most famous one is this one, also known as Cramer method, which solves linear systems of equations. But now the point is, yeah, let me skip this. This is the example for a 3x3 matrix. The idea of that example was that even with small matrix, all the stuff is different, is quite, it's a bit complicated to implement. So implementing it manually is not a good idea. So let me skip this, because the aim here is that it's not necessary to reinvent the wheel, because NumPy offers us all the stuff, and it offers the inf function, which is available and works very well. But finally, the most important thing is that, yeah, it's the same thing, but I think that the most important slides miss anyway. So the idea was to check out at the documentation, because if you see at the documentation of the inf function, this one, you will realize that the inf function is not is just a wrapper function to another function, which is the solve one. So basically meaning that the NumPy implementation of the inverse matrix uses the Crumbler method. So the suggestion now, the last suggestion I may give you is to look at the documentation of these libraries, such as NumPy, SciPy, which is really, really well done. So really informative. So that's all, and thank you very much for your kind attention.
Thank you very much to both of you. And any question? I think it was a hard topic.
Yeah.
Only about the distance that you had to rewrite the function. It was not possible to map the Euclid with your distance, if it's linear.
Well, actually, the problem in that case was that we have to clusterize points on a map. So the distance, we may not apply the so-called Euclidean distance because we are not in a 2D space. We are moving on a sphere. So the distance function we have to use is the so-called sphere distance, which is calculated by that formula. And the point were that the SciPy implementation of k-means does not allow you to pass a function pointer to the function, so you have to do the clustering, you have to re-implement from scratch the algorithm. So that was the problem. Yeah, not a big deal actually.
Any more questions?
In order to re-implement the k-means function in order to do your clustering, well, I think you re-implemented it in pure Python, right?
Right.
And using NumPy for optimization.
Exactly.
Does NumPy offer also some C-level interface in order to re-implement such kind of functions at the C-level and then expose it?
Sure,
Okay.
sure. Actually, in the SciPy library, there is, actually you may implement your code using the C++ code, you may use the Fortran code, and the NumPy, and I don't know if NumPy, but SciPy for sure, offers you some stuff to directly compile the code you wrote on these languages. For instance, for the C++, there is the Wave library, I guess, the Wave library. So, and the Wave library has an inline function that allows you to pass some snippet of C++ code, and it actually, under the hood, calls the GCC compiler, or the compiler you specify in the inline function, and it works. But actually, I don't know about performances.
Hi. You said that NumPy is fast and Python is slow. But how fast is NumPy? I mean, if we install it, do we get just plain i386 code, or you know, vector operations that got added in late 90s or so, or can we get these massively parallel vector calculations done in graphical processors?
Oh, well, yeah. Actually, the point of the case study was to not explicitly iterate on NumPy arrays. So if you have to deal with NumPy arrays, maybe using explicit loops is not a good idea. That was the point. Then about the exploitation of the graphical user interfaces, well, I think
it's about GPUs.
Yeah, GPUs. So, but I didn't get the point.
Graphical user interfaces.
Yes. So, what was the question? About? Yeah.
Oh, just a moment.
Sorry.
What level of, I don't know, optimization do we get by in a standard NumPy installation? Will MMX instructions be used? Will the later generation vector operations be used? And can the GPU operations be used by NumPy?
This kind of depends on how you compile it. I mean, under the hood, NumPy calls some BLAS implementation. So, depending on how you compile these, you're going to get different performances. For example, the guys from EuroPython bundle NumPy with the MKL library from Intel. That is very, very fast on Intel hardware, okay? So depending on how you do things, you get different results. And usually NumPy tries to find the more efficient implementation viable for your machine.
Thank you.
Anyone else? Okay, here.
I get the sense there's something clever going on with the vectorize, but you sort of skipped over it and didn't go into any detail. Can you explain a bit more how that works?
Okay, basically that's about higher order functions, okay? The idea is that you can take a function and apply that on every element in the matrix. Since under the hood you can consider every matrix like a linear collection of elements depending on how you travel them, okay? Any matrix, any n-dimensional arrays, that's the basis. And you can use this vectorized function and give it a function that takes any number of arguments and has an output argument as well, okay? And then it returns a function that applies that element-wise on each element of the matrix, and that can be done at sea level. Okay, basic, almost. So you don't have the vectorize does not just def aux 4e in shape, 4j in shape, 4k in shape, do that, okay?
So is that saving anything over the sort of normal Python overhead for a function call?
I think so as well, yes.
Oh, maybe one quick question. So, is it quick?
Just an answer. Maybe it's related also to bound checking on the arrays, because if you pass them as an array, you don't have to check the bounds for each increment of the index.
I really don't think so. I mean, bound checking can be really a performance hit if you're doing very, very fast stuff. So, for example, C decides not to do that by default. But anyway, I think the very idea is that iteration in Python has got some overhead, because you got iterators. You call the iterator, you get the next method of the iterator, you return the next element. It's a very, very high-level interface somewhat, and that can be done at a very lower level. Okay.
Okay. Time is running up, so thank you very much, Enrico and Valerio.